Welcome everybody to this week's Ask an Astronomer episode. We are here to answer all your questions about science, the universe and everything. And today with me I have Nina. Do you want to introduce yourself and talk a bit about what you're doing and what's your field you're working in?
Yeah, sure. So my name is Nina, and I'm a postdoctoral student in the University of Cambridge. And I have done many things in the past. So I've worked in massive star formation, and right now I'm working with objects that are called Xray binaries. So those are binary stars, so two stars that are orbiting one another. And one of those stars is a compact object, so something that is very, very dense, something like a neutron star or a black hole, and that is accreting mass from another star. And due to this accretion, these stars emit a huge amount of X-rays, and that's why we call them X-ray binaries.
Oh, okay. So basically this accretion is this like mass flowing from the pieces of the one star flowing into the black hole.
Exactly. So one star is too close to the other one, so the gravity from one star just starts pulling material towards itself. And in this process, as it pulls material off and it accelerates due to the gravitational force of this compact object, then it ends up hitting very, very strongly, and it starts emitting in the X-rays.
Oh, that's cool. Okay, so I should also say I'm Stefan. I'm also a PhD student at Cambridge, and I'm working in cosmology. So I'm studying kind of how the universe evolved, and in particular how the first stars ionized the universe. So how it transitioned from a neutral, more or less boring universe to a exciting, burning thing that we have today. And you can just ask us anything you want to ask, like if it's about the work we're doing or something generally about astronomy or science. Go ahead and put it in the YouTube chat, or if you prefer on Slido, that you don't need an account. Or if you're watching from Twitter, you can also use the Periscope chat to send us questions. And while you're busy typing the questions, I'll just get a few from the last stream where we had quite a few questions that we couldn't answer. So there were a few questions actually in the past about galaxy form evolution and how the different shapes of galaxies exist and why some of them are older and younger. Maybe you want to give us a bit of an overview there, because I think, I didn't explain that too good in the last time.
Okay, so usually we have galaxies that are very, very active, and they're still forming a lot of stars. So one example is the Milky Way. So the Milky Way is a spiral galaxy. And if you look at the spiral arms, those were the places where you find giant molecular clouds, which are the places that are the stellar nursery. So that's where the stars start to form. And every time that you form new stars, you form a bucket load of stars. You form very small stars and very big stars. But small stars and big stars, they shine light in a slightly different way because they have slightly different temperatures. So as a result, they shine in different colors. So a very good example is, for example, if you look at Orion, and you look at the constellation Orion in the sky, and you look at Orion's shoulder, there's a star that's called Betelgeuse, and that star is very, very, very red, and that is a red giant. But when you form a very small stars, they are also red. So you can see that what Stefan changed now, the picture, is what we call an HR diagram. So that shows how stars evolve through their lives. So what you can see is that on the right-hand corner there are the tiny stars. You can see that the size of the stars are in proportion. So the tiny stars, they shine more in the red, whereas the bigger stars, they shine more in the blue. So if you're taking a galaxy that is very young, it's gonna have this very big blue stars, and it will look more or less bluish. Whereas if you have a galaxy that's very old, most of the big stars, because big stars, they live less long as small stars, all the big stars will have died, but the small tiny red stars are still going to be there. So those galaxies, they will look redder. So usually redder galaxies, they're older galaxies, and bluer galaxies, they are younger galaxies.
That's cool. While we're talking about galaxies, we just got a question from YouTube. Are there any ultra-faint dwarf galaxies observed which have evidence for active star-forming regions? So I don't even know what an ultra-faint dwarf galaxy is, but probably you know that better than me.
So there are I don't know if ultra faint dwarfs, but there are dwarf galaxies that have star formation going on. Dwarf galaxies are slightly different from the Milky Way because they're much smaller in terms of how much mass they have. So they don't have spiral arms in the same sense of the Milky Way have. So they're a slightly different shape. Yes, and so in a way they do have active star forming regions sometimes, yes.
And I guess they're faint, I guess they're like fainter when they have less stars, or is it just because like are dwarfs in general fainter than normal galaxies?
Well, they are fainter because they're small, so even if they have a star forming burst, they don't form as many stars. So the amount of stars you form is always proportional to the amount of mass you have in your galaxy.
Yeah.
So if you have a huge amount of mass, you can form lots and lots of stars. And if you don't have a lot of mass, then you're going to form less stars.
Does it also change how massive the stars are you form? Like, let's say a really large galaxy with lots of mass. Do you form more massive stars, or is this not related?
It can be related in some ways, but in general, we believe that as long as you have a certain thing that we call metallicity, so that says how much metal-rich your gas is. And here we're talking about astronomical metals, so it's how astronomers call anything that's not hydrogen and helium. And these metals, they help your gas cool. So usually star formation obeys these metallicity rules. If you have a very metal poor gas, then you can usually form bigger stars because you're not able to cool your star efficiently to form the tiny ones. But as soon as you have a certain metallicity, you can usually form both massive and less massive stars. You are always gonna form, on average, smaller stars today than you're gonna form bigger stars, just because you have to accumulate a lot more gas to start forming those big stars. Right, so it's imagine that's a house and you have to accumulate enough money to buy it. It's easier to buy a small, studio than it is for you to buy a mansion or a castle. So it's kind of the same thing.
Yeah, that sounds reasonable. One question we got also from last live stream was, what is the biggest concern for astrophysics right now? And I think that's a question where we can probably both have some comments and probably different opinions because we're working in different fields. And I think the question will probably depend a lot on what you're working on and what you would like astrophysics to do. So do you want to start maybe?
There are so many things. That's a very tricky question. I mean, if you look at anything in detail, we don't know the particulars of almost anything, and that's why we can keep ourselves employed in a way. But I think, I don't know, the biggest challenge. I think the biggest challenge is probably related, I think, to cosmology and knowing what, for example, dark matter and dark energy are. Because it's supposed to fill most of the universe, and we are still pretty much, on the taking baby steps, towards trying to figure out exactly what they are. We have a lot of clues of what they do and how they alter things, for example, like the CMB.
Oh, yeah.
And structure and how you form stars and things like that. But as of exactly what they are, that's pretty much still, I think, an open question. What do you think, Stefan?
Yeah, I mean, I'm working a lot in cosmology, so of course my view is a bit centered around I want simulations, like large simulations, and basically there's always a thing in simulations. You kind of, let's say you want to simulate how does the matter in the universe like form galaxies eventually, right? So the universe starts out as like a large field. Actually, I can show you a nice simulation of this, which is called the millennium simulation. Here we go. And the universe is kind of a big cosmic graph, right? And then the structure kind of falls together slowly. And when it falls together, it might form galaxies, and then the galaxies form stars, etc. And those stars might explode eventually, because that's what stars usually do when they die and they're big enough. And these explosions, of course, mess up all the nice, like, slow, nice stuff falling together part. And we can't simulate everything in here, right? So when we simulate like thousands of galaxies, we can't simulate all the gas in each of those galaxies. So what we need is some kind of models of, okay, let's just say here's some gas, and let's just say, okay, on average, the supernovae maybe reduce the clumping of gas by a factor of this. But for this, we need really good models, and I think they are like, we are having there's a lot of work to be done and a lot of improvement possible on kind of these models, and how can we include all those astrophysical details that we, in principle, kind of know about, or at least could simulate, but just in practice, there's no way to do that. So there's just a lot of things to be done.
Yeah, definitely. I agree a lot with what you say there, especially because, for example, this picture that you're showing, this picture is 500 megaparsecs. It's huge. So if you take a little like yellow point there, that's gonna be many galaxies. So and one of the difficulties we have with simulations like the millennium simulation is you can't zoom into endless smaller scales. So for example, like Stefan just said, when a star gets to the end of its life and it goes if it's a massive star, it usually goes supernova. And when it goes supernova, then it throws gas away, and you could say that, oh, okay, so it's throwing gas away, so it's stopping star formation in a certain way, yes. But in another way, we also know that supernova create turbulence, and that this turbulence helps also compress gas, which also helps form stars. So it's a very complicated, intertwined process in terms of this supernova, the energy that stars, like radiative energy that the stars throw into their surroundings, all those processes that stars put matter or energy into their surroundings is what we call feedback, stellar feedback. And in some ways, it acts against the formation of new stars. In other ways, it acts in favor of the formation of new stars. So it's very complicated, and there's a lot of debate on like, which one is it? Is it helping or is it making it worse? And we still can't do a simulation where you can see the whole world in terms of a cosmology, and then keep zooming into galaxies and then zooming into a particular star, into a particular solar system to see exactly what is happening everywhere. And that is a bit of maybe a dream away, but definitely when we get there, it's going to be really cool.
Yeah, when you're ever sitting in the simulations talk and someone tells you about the simulation, you can always ask a question, did you consider feedback? and you can annoy the person. We got another question from YouTube. Is it possible for there to be Gammaray binaries? So we talked about Xray binaries before, so kind of binary stars that produce lots of X-rays. Does it also work with gamma rays, so more higher energetical radiation?
So definitely in terms of like, you can accelerate material so that you also emit gamma rays. It's more a question of, for example, even X-ray binaries, they emit some amount of gamma rays. It's not the most radiation that they emit. So whenever we say like a star emits a certain, for example, the sun, we perceive it as being yellow, right? Because that's where most of the light is shining is, in a way. So it's the optical, the things you can see is no accident that it is exactly around the color of the sun. Your eye adapted and evolved so that you can see where the sun shines most light. But for example, that the sun also emits X-rays, and the sun emits other things like UV. Otherwise, you wouldn't need sunscreen when you go to the beach. So in general, you have binaries can emit in almost accreting objects. In general, they can emit in almost any wavelength or light frequency, but it's going to be in different proportions, and we tend to name them based on basically the one that they emit the strongest. But for example, if you have something like a gamma ray burst, that's also an accretion process. in a way,
Oh.
where you have like very strong emission of material through a pole of something of a accreting supermassive black hole. So in a way, yes.
So can you so X-ray binaries, they have this like kind of this peak in X-ray, which is why they call them X-ray. But can you also does this peak shift around depending on what kind of X-ray binary you have? And could you shift it around enough so that it would be kind of at its maximum in gamma rays?
They can't have their peak exactly in gamma rays, but they do shift their peak depending on how they are accreting or how much they are accreting, and basically the whole environment around the binary itself, because the gas around the binary also can reprocess the light this binary emits. So these binaries can usually change from having a peak in the soft X-ray to a peak on the hard X-ray. So it's boring the terms that it stays in the X-ray range, but the X-ray range is actually pretty big. So yes, for those ones in particular, we're mostly concerned in the X-rays. But sometimes they go quiet in a way, and they are now having more ample surveys where they're trying to look at these X-ray binaries not only in the X-rays, but for example also on radio, actually to try to understand how they work better. Because sometimes when they stop emitting in one channel is because they started emitting in another, and it's very hard for you to get, because usually you have a telescope, and that telescope is very specialized in measuring wave at a certain frequency. So when you are trying to study X-ray binaries, it's very common that you go and you just take your X-ray telescope and you look at that in the X-rays. But then for you to do simultaneous observations also in the optical, also in the radio, also in all the other categories at the same time to see the whole picture, that's rare, and that's something that we're still also just starting to do to try to get a better concept of what is truly happening.
While we're talking about the topic of telescope, we got one question also before the stream. How helpful will JWST be for your studies? So maybe I should say what that is. JWST is the James Webb Space Telescope, built by NASA, if I remember correctly. And it's actually, I think, a bit delayed. So it was supposed to launch at some point, but it's a bit delayed. So it will, well, there's a bit of a kind of meme that JWST is always delayed. But it will launch eventually and be a new kind of the successor of Hubble, kind of, in a way, and make better and like more accurate pictures of kind of the sky. So are you will you use JWST? Do you plan to use it in any way for your research?
Oh, I plan to use whatever comes out of JWST in terms of it's I don't know if that is a correct way of saying it, but it's kind of an improvement on Hubble. So it's gonna have a lot of new data for a lot of use in terms of unveiling star formation to characterizing galaxies and things like that. So there is gonna be something there for everyone. Basically, all the areas you study. So definitely some of the data that comes from JWST is gonna help in my research. I'm not an observer myself. I work in doing simulations, but people that do simulations, they always have to they can't just go into their world of their own of computational science and completely forget about the real world of astronomy that is out there. So you have to eventually reconcile the two and try to see if your simulations are actually reproducing the real world, and also take things that we observed from your real observations and trying to slowly incorporate those in your simulations and make them more complex. So I think that is going to be a huge help.
Yeah, I mean, I'm also kind of interested in the part of kind of how did I mentioned the first stars and actually also the first galaxies, how did they affect the universe? Like, in what way and when did they get created and how large were they? And that's also a thing that you, I think, can see with a space telescope. So you can make observations of really old galaxy. And of course, with JWST, I think you'll reach quite a lot further than with Hubble. So we might actually have a chance at kind of observing the first-ish galaxies, which would be really cool to see. how they look like, and if they're different. Yeah, while we're talking about hot topics, one person who is like kind of an upcoming astronomy student asked, what's the most interesting kind of field in astronomy kind of right now or in the next decade or the next, well, the future?
I think that's a very subjective question.
Yeah,
right?
yeah. I mean, there are some fields that are, I would say, objectively like, I mean, so in general, kind of fields, there are fields that are really new and kind of where like lots of exciting research is happening, and there are fields that have been around for 100 years and where there's still exciting research happening, but maybe not that much or that new things. Like, it's less kind of surprising. It's more like, okay, we already knew what to do, and we'll just improve upon that.
Yes, sure. I think in terms of new things, I think definitely fast radio bursts, or what people usually call FRBs, are one of the hot topics. So those are fraction of a millisecond long radio bursts. From the name, you can kind of figure that out. And their source is completely a mystery. So we have no idea what creates this fast radio burst. There are lots and lots of theories. There are some very good candidates, but there is nothing that we actually pinpointed there. But the interesting thing is that even though we don't know what they are, because when they travel through the universe, their light gets dispersed. We can actually measure a lot of very cool things with fast radio bursts. So I know, Stefan, you're also working on that.
Yeah,
so maybe
yeah.
you wanna add a few.
Yeah, like the great thing about fast radio bursts is that they are like so bright, and we can see them to probably really far distances. Which of course directly there as a cosmologist, right? You have far distances. You can see, oh, how does the universe evolve? Like how did space evolve in between? Like does it kind of distance and the age of this fast radio burst match with what we expect? And can like do tests of does the universe actually expand the way we think it does? Or maybe we can find out more about dark energy that makes the universe expand faster and faster as time goes on, which is a huge mystery and might be solved. Well, not solved maybe, but we surely can find some great clues with fast radio bursts. We just got a question from Twitter on Periscope. Does radiation pressure counteract neutron degeneracy pressure in white dwarfs to keep them from collapsing into a singularity? Oh, that's a nice question.
So in some sense, no. So what you're trying to, the degeneracy pressure is in a way a quantum mechanical effect. So and that's what is keeping actually it from collapsing into a singularity. So it's the degeneracy pressure is the one that's opposing gravity.
So
in that sense.
Right. So basically, kind of, let's just give a quick talk about kind of small objects. So the smallest and heaviest thing you have in astronomy are black holes, right? So they're just really, really massive, and because kind of light cannot escape from them, they're super, super heavy, and that's why they look black, and we don't know what's inside them. And then kind of the next step up from that is a neutron star. So that's basically an object that's basically like a big atom core, just in like star size. So basically it's just full of neutrons that are kind of really stacked very densely. We actually don't know exactly what behavior they have, like what pressure, etc. It's inside. That's actually a topic of research, which is called the equation of state of neutron stars. There's a whole bunch of research behind there. And they are actually, I think, there's the ones that are supported by the degeneracy pressure from neutrons, right? Correct me if I'm wrong.
Yes.
So basically that's a quantum physics effect that you cannot have too many neutrons in the same place, just by the kind of laws of quantum mechanics. They have to be different from each other, which is why they are kind of in different places, and that makes a thing not collapse into a small object like a singularity or a black hole or whatever. And in white dwarfs, it's not the neutrons. So is it electrons or is it any kind of radiation? I think it's electron degeneracy pressure.
It's electron degeneracy, yes.
So it's basically the same thing as with the neutrons, just that you don't have only neutrons, you also have electrons and protons, which makes the whole thing a bit larger because electrons are kind of lighter, and basically that makes your star larger. And if you have a white dwarf and you make it more massive, at some point those electrons and protons combine together to neutrons, and that's why it then collapses into a neutron star. And everything up from white dwarf, so everything that's a star and kind of burning, is supported by, as you say, radiation pressure. So that's basically the star is burning in its center, and all the light wants to go out, but collides with, well, the star that's in the way. So that's kind of like makes a star large. Like that's the kind of thing that supports a star. Did I explain this roughly correct, Nina?
Yeah, no, it's absolutely correct. So as Stefan is saying, so as long as you haven't, your star hasn't died. So white dwarfs and neutron stars and black holes, they're all the end, phase of a star. But when a star is, for example, in the what they call the main sequence, or when it's red giant, so if you remember the HR diagram that Stefan was showing at some point, so all the stars that are kind of in the upper half of the, so if you take a diagonal, the kind of right top half of the, they all counterbalance gravity due to radiation pressure. So, for example, that's why when I said that big stars, they live less long, because they have such a big gravitational force that they have to burn much more effectively the fuel in their core to just keep themselves from collapsing. And that's why they evolve faster. Whereas small stars, they don't have that much gravitational pull. They don't have that much gravity to counteract. So they can make do with burning, hydrogen into helium in their core a lot slower and still survive.
Okay, also and hello to the new viewers on YouTube. We'll get to those questions in a second. Just that we got just a follow up from the previous question. Is it likely that the phantom event horizon exists inside white dwarfs? And so before, okay, I'll talk about event horizon in a second. Let me just put a small disclaimer. This kind of approximate formula of, oh, there's always an event horizon which is just 3 times the mass basically of an item times like speed of light and a few constants, works in most cases, but there's some cases like very close to the Big Bang where this formula doesn't work and you actually have to kind of look at the system. We had a discussion about that today and with some cosmologists. I might talk about this later or next week. And back to the question. So for kind of stars usually, or for the kind of general spherical small round objects, you can say that the event horizon is proportional to the mass. So the event horizon of, do you know the event horizon of the Sun or Earth by heart? I think it's like a few centimeters or kilometers or something. So it's much smaller than the Earth or the Sun itself. But if the Earth would be like, I don't know, a centimeter large, it would be kind of a black hole. So that's, you could say, the event horizon of the Earth is, I don't know, this many centimeters. And you could say the same for, say, a white dwarf or a neutron star. But since the star itself is larger than the event horizon, it's not a black hole. So basically you can say everything that is smaller than its event horizon is a black hole. So if something collapses that small, then the kind of density is high enough that you get this black hole effect of no light can go out, no information can go out, etc. Yeah. We got a few more questions on YouTube, so let's start there. What role does the circumgalactic medium play in star formation? Do you know that, Nina? Because I'm not an expert.
So gas falls, like the way that you form stars is by gas falling into your galaxies, right? So there, in a galaxy like, for example, the Milky Way, material constantly is being thrown up from, for example, supernova explosions, and then it can fall back, can have this kind of fountain effect that we call. And once gas falls into the galaxy itself, it can cool down, it can, join into molecular clouds, and then it can give rise to star formation. But yeah, what mainly controls star formation is this big clouds that have a much higher density than most of the galaxy, where you have these regions that are turbulent, that form this kind of filamentary structures that are very dense, and it's there that you actually start forming your stars. So for you to form a star, what you need is basically a very dense and very cold place in a molecular cloud, and then you're ready to basically start the star formation process.
Oh, that's cool. And thank you for the update at Xabyss. So we just got it from chat, the update. The Schwarzschild radius of the Earth is about 1 centimeter cubed. So if you would take the Earth and compress it to 1 centimeter cubed, then it would be a black hole. And for the Sun is a few kilometers. So I think for a white dwarf or a neutron star, it's also in the order of a few kilometers. So I think, what's the size of a neutron star? I think it's like a bit more than a few kilometers, but not much more, right?
Yeah, it's about the size of a large city. It's about like 10-20 kilometers.
The size of a large city. That's just a great description.
So imagine you taking a star much, larger than the sun and compressing into the size of, maybe New York or something, and that's basically your neutron star.
Okay, let's not do this in the real world. But yeah, okay, so right. So basically, the neutron star is like, let's say 20 kilometers large, and it has a Schwarzschild radius of maybe like, I don't know, 2 kilometers. Then it's not a black hole. But as soon as you would compress it strong enough by, let's say, making it more heavy, and then it would kind of, at some point, the degeneracy pressure wouldn't help anymore, and then it would fall together. Okay, so next question. Why does strange matter convert everything it touches into strange matter? I'm not aware of that strange matter. And why do the more rare quarks downgrade into up or down quarks? Ah, okay, I think what you're meaning is probably strange quarks, or like in general the let me get a particle physics standard model up here. So the quarks like charm, strange, top and bottom, which are the kind of heavier quarks than the normal ones up and down. Let me give a short introduction here for those of you in the audience and in the stream that are not particle physicists. So our model of kind of elementary particles is that everything consists of so-called quarks and leptons and a few other not so important particles. I might have insulted some particle physicists by saying gauge bosons are not so important, but basically the matter is made up of quarks and leptons. Leptons are basically electrons in neutrinos and similar families, and quarks are kind of what makes up the atom core, so what makes up our protons and our neutrons. And all the normal matter, like your table, your average person, will be made up of up and down quarks. They make the protons and neutrons. And there will also be a few electrons that are flying around in the atoms. But you also have kind of the heavier variants. So, for example, in cosmic rays, you can find muons, which are basically like electrons, just heavier. And even taus, which are even heavier. And the same goes for the quarks. So you can also find strange charm quarks, which are kind of the equivalents of up and down quarks, similar electric charge, just more heavy. And then again, top and bottom quarks, which are even more heavy. And we can produce those, for example, in particle colliders. So, for example, at the Large Hadron Collider in CERN, you can send particles around kind of a magnetic ring really fast. And when they collide, you get lots of energy and produce lots of kind of particles that basically everything you can make out of energy. And when you would say have a charm, so you can build, of course, a kind of nuclei, so atomic, kind of, you can build the equivalent of protons with other things. We call them then, like, there are various names like Hyperion, and I can't even remember all the names. But basically, you can have this, for example, you can have two up quarks and a strange quark, and that would also be some kind of particle. And as soon as you kind of add some of those non-standard objects into the particles, I'm not sure if you would call them strange matter, but they are certainly get different names. And I think that's what you're referring to. So as soon as you have one of them inside you or your atom, it has a different name. It behaves differently and has different properties. And it doesn't, like, it's not really that it kind of everything that it touches is changed, but it's just if you take one of those, like if you just change a single particle in your atom, it just behaves differently, which is why it's a different thing. And the converting and decay into kind of downgrade to smaller quarks is mostly just because they're lighter, so you kind of save energy. Let's say you have a muon, which is 105 mega electron volt. So electron volt is the energy unit. So basically the kind of the mass, the energy cost of a muon is 105 million. And an electron is only 500,000. So you can convert a muon to an electron. It's not that easy, but a muon can decay into other lighter particles, and then you get free energy. And this is a reaction that usually happens in nature, so it takes, I think, what is it, a microsecond or so, an average, for a muon to decay into smaller particles, or into lighter particles, which is what usually happens. That's why everywhere around us you only see up and down quarks and electrons, because those are the lightest of the respective family, and that's what's left over after everything else decays. Okay, that was a lot of particle physics. If anything was unclear, please go ahead and ask follow-up questions in the chat. While we are at this, so next question was, is it possible to place DNA particles into the probes and control their evolution? Will space radiation destroy them, gamma and X-rays? So I think what you're referring to is space probes, right? So you want to put some DNA or other material into a spacecraft, I suppose. You could put humans into rockets. And what will space radiation do to that? I know a bit about that, but maybe do you know more, Nina?
Well, it's a big problem in terms of trying to know how to shield yourself completely from radiation. So, for example, we've never really, for example, the radiation that you get from going to the moon is a lot smaller than the radiation you would get from, for example, going to Mars. And the problem is that the sun has a lot of very fast charged particles, which we call the stellar wind, and you're just being bombarded by them literally when you are outside of the Earth's nice atmosphere that protects you from everything else. And the problem with that is that as soon as you're getting bombarded by these particles start destroying your DNA chains. And then when your cells try to divide again, to do I think every 10 years you have to rebuild every single cell in your body, almost.
I think so.
By division. And then the problem is that what happens is something very similar to what would be cancer. Because you screwed up the DNA within that cell, whenever it's trying to do its division, it doesn't work as effectively anymore. So that's very dangerous, for example, for sending astronauts into space. So that's why you need very good spacesuits. You have to do a lot of trials of sending other things to space, DNA samples, bacteria, and see how they survive to those levels of radiation, measure those levels of radiation very accurately before you're thinking of sending real people down there, because the results can be pretty devastating. But in terms of controlling their evolution, I don't think that's something that you can do by throwing them into space or anything like this. It's something that you could try to do maybe on Earth, but that's probably a better question for biologists rather than to astronomers. So
yeah, I mean, but if you want to kind of the DNA of a cell to mutate, it's much easier and much easier to control if you just put them next to a X-ray device on Earth, or you go to a particle collider, and they are you don't need to go to CERN. There are lots of smaller-ish particle colliders that can also produce X-rays, and they basically can say, oh, I want this particle to be shot at my cell, and you can arrange this. And this is much easier than sending something to space and just hoping, well, whatever happens. So if you want to do a controlled experiment, we can produce all the radiation on Earth, well, most of the radiation. So that's kind of usually the easier option, if that's a goal. The next question on the chat was about Hawking radiation. So that's also a question we get very often, which is a great question. So let me show you a simulation of a black hole to illustrate this a bit. So on this black hole, you have this event horizon, and what you can imagine is kind of the surface where nothing can escape from. So as soon as something is inside, it can't get out because the gravity is just too strong. Basically, the space is curved, and that stops it. But just imagine it's just pulling too strong, which is more like an analogy, but it's fine. So, and what these black holes do is they emit radiation. So we think they do. So we think that every black hole that is out there will send some radiation, just kind of particles that are flying away from its surface. And that's called Hawking radiation. And the reason for that is, due to quantum mechanics and the Heisenberg's uncertainty relation, you can borrow a bit of energy from the universe as long as you return it fast enough. So what you can do is you can just have two particles get created in the vacuum, be there for a really short time, and then they annihilate again. The energy is gone again, and you're fine. The universe allows that, as long as you are doing really short and it doesn't do anything. The trick is now, when this happens, so this is, I should say, also more like a, it's not a really mathematically like very accurate explanation, so that's kind of the intuitive explanation, but it's not actually what happens. But I think it's a good analogy. So what can happen is that this process appears close to a black hole. And if you imagine, let's say this appears on the surface of a black hole, and you can create those two particles, and you would have to return them back to the universe in a millisecond or so. But one of the particles falls into the black hole and doesn't know about the other anymore. Then those two particles can't kind of reunite and annihilate, but are free. And then the one particle that's outside of the black hole can fly away, and we can see it as Hawking radiation. And now, to clarify this kind of approximation, disclaimer, this doesn't just happen at the surface of the black hole. This happens kind of around the black hole and also a bit further away. So just everywhere where there's a very strong curvature of space. And it's basically a quantum field theory effect when you do the math with curved space-time. I can't do it myself that easily, but it's a math you can do, and it's not that exotic. So that's something we're quite sure that happens. And actually what this does is it makes black holes evaporate and die at some point. So when you have a really small black hole that doesn't have much mass, this effect will actually cause it to evaporate within seconds or even milliseconds. For larger black holes, this takes billions of years, so they are not that affected. But that's the thing, because this energy that you the radiation you send out, energy is still conserved, so the energy has to come from somewhere. And usually it feeds off the black hole. So the black hole loses a slight amount of mass through this Hawking radiation. And yeah, that's what Hawking radiation is. We didn't detect it yet, but we are pretty sure it exists. But it will be really hard to measure, because we would get really close to a black hole, and we don't really want to do that, and also we can't do that really well. So it's a question for the far future, I suppose. Let's get another question from Periscope, which was, can we detect B-mode polarization with a gravitational interferometer like LIGO, but more sensitive? And to clarify, by B-mode I meant primordial gravitational waves due to inflation. Sorry, Nina, we'll get some non-cosmology questions for you soon. I see already some non-cosmology questions on YouTube. So what we think is the universe started kind of at the very beginning with what we call inflation. So a large period where the universe expanded very rapidly, and there were lots of quantum effects going on, and those effects depend on what exactly inflation is like. But usually we expect that whatever happened did send out some gravitational waves. So gravitational waves are basically waves of gravity that travel through space. And what they do is they stretch and make space a bit shorter and longer in various directions. So just imagine a gravitational wave would pass through your door. It could make the door, for a really short amount of time, a bit less high, but a bit wider. And this would be not noticeable at all for you. Like, it would be less than a proton diameter in change. But it is something we can measure when we build really accurate devices. So actually I have a picture of a gravitational wave kind of observatory here, which is LIGO. And they have just two really long tubes, 4 kilometers, filled with vacuum, and a laser inside that measures the distance between, like, the length of the tube. And they have those two tubes, like, in a right angle, and they can measure the distance and notice a change in distance when a gravitational wave passes. And this is really cool. Like, gravitational waves, to actually measure them is really fascinating. And currently we are measuring mainly, well, actually only gravitational waves from merging black holes or merging neutron stars. And right, the question about so these primordial waves in the beginning of the universe are much weaker, so they are much harder to measure, and also in different frequency range. So I'm not exactly sure. I'm not sure if you know that, Nina, what frequency-ish they are at.
I don't know what frequency LIGO is detecting, but I don't think it's gonna be able, at least on the current. So even some types of measures of stars, it still cannot resolve due to sensitivity.
Okay.
So let alone something that comes from. I mean, I'm not an expert in B modes from inflation, so.
Yeah.
But I don't think it's something that we can detect right now. But I just wanted to add that LIGO is an incredibly cool experiment in terms that, in some ways, it's extremely simple. The basis of what LIGO is actually very similar to another experiment that's called the Michelson-Morley experiment, which was actually one of the experiments last century that proved that the speed of light was constant. And Morley actually got the Nobel Prize for actually, showing that the speed of light was constant. And he was incredibly frustrated because he was one of those people that believed the existence of ether. So he got a Nobel Prize for proving he was wrong in a way. But the idea is that it's an interferometer. So the idea is that you put two laser beams and they are interfering in a certain pattern with each other. And then, because of what Stefan just said, if so you're keeping having this pattern as long as they are always, imagine that you have your wavelength. If your wavelength is always arriving at the same point here the same way, then it's always giving the same interference pattern. Now, if there is a gravitational wave.
Oh, welcome back, Nina.
Hello.
We're back. Yeah. Can you hear me? We can hear you, so that's fine.
Okay.
Interferometers.
Yes. So I don't know up to what point you listened. Sorry about that. So basically, what you just get is they interfering, and then when this one of the lasers basically changes slightly its wavelength just because of this compressional space from the gravitational waves, then you can detect basically merging black holes or merging neutron stars and things like that. So it is pretty simple in this way, but you also have to kind of isolate from every single possible vibration on Earth, everything that could change that laser that is not an astronomical source. So that effort has been what kind of revolutionized our way of doing astronomy. So it's just pretty cool. I just wanted to say that.
It is, yeah, I totally agree with that. And so back to those inflationary, so those waves that come from the beginning of the universe, actually further back than we have ever seen. I think we need a thing in space to measure them. So, for example, LISA is a proposal to build such an interferometer in space, not by building two long tubes, but just by putting 3 satellites into space far away from each other and measuring their distance between each other constantly. And I think that's gives you actually the right frequency range to probe this. So LIGO can probe gravitational waves that are from the frequency kind of like in the range of human hearing. I think it's like a kilohertz order of magnitude, while LISA can probe a different order. And just one update on the kind of DNA things. So there are different types of radiation. We just got the note from the chat. Thanks you for that. Alpha particles. So that's kind of atom cores that are part of radiation, radioactive radiation, for example, or other kind of radiation. And they can kind of affect the DNA, so they can switch things around or break pairs or make new pairs. And alpha particles are also things we can produce in the lab. But usually when you're talking about higher energetic photons, like gamma rays, that's usually, gamma rays are usually photons, so that's also part of radioactive radiation, which is basically just a really fast photon, which can kick something out or destroy some atom or molecule. Alpha particles are these atom cores that are flying around, and lastly, beta particles are is it positons or electrons?
It's electrons.
Electrons that are basically really fast and also can go fast and destroy things.
So alpha particles, in a way, they do more damage just because they're more massive.
but you can shield alpha particles really easily. So you can just put a piece of paper in front of your spaceship when you're an astronaut inside,
Sure.
and alpha particles won't get through. And beta is also quite fine. You can just put a bit of aluminium in front. But gamma is really, really hard to shield against because it's just a fast photon. And when you build a barrier, it will just kick the barrier and kick something out of the barrier. So that doesn't really help you. It's actually a problem. You need basically a big block of lead. And the problem with a big block of lead is it's really, really heavy, which means it's really, really hard to bring to space. But luckily,
also try going on, once you have to train with spacesuits and things like this. The spacesuits are incredibly heavy. If you ever get a chance to see one, they are like the full suit is a major thing for astronauts to train. They have to go in this huge swimming pools and try to walk just one length of the swimming pool is a huge, physical effort for them, just because they are so heavy, because it has to be able to protect them from all the radiation.
Okay, let's get some star formation particles for Nina. How cold is a cold gas in which stars form? What is the upper limit in terms of temperature in which star formation is inhibited? Is one question we got from YouTube.
Okay, so usually the coldest regions of these molecular clouds where the stars form, it's around 10 degrees Kelvin. But obviously, as soon as you have, so imagine that you have, for example, a filament, and this filament is very cold. And because it's very cold, is what is usually going to be molecular. It's not going to be atomic. And then it forms like a little ball where it starts attracting things due to gravity, just to gravitational force. Then we have what we call a protostellar core. And this core starts, contracting due to the force of gravity. But as it contracts, it loses gravitational potential energy, and it starts increasing its temperature. And that's when the metals that I told earlier on about cooling come in. So they help this contracting core start to cool down, right? So that it can contract more and more and more and more. So obviously, the core of this protostellar core is only going to become hotter and hotter and hotter. And basically, once it's hot enough so that you can basically start merging hydrogen nuclei, then you can start fusion, and that's when you get your star. But for example, if you have temperatures of thousands of degrees Kelvin or thousands of degrees Celsius, then your gas pressure, because as you increase the temperature, your gas starts moving at a higher speed, right? So they are able to counteract gravity way too well, and then you never get this contraction anymore, so you can't form stars anymore. So your gas has to be cool to start with, and then is slowly being able to cool as soon, and then eventually at the core be hot enough so it can form a star. That's that.
Okay. And the next follow-up question to that, what is the main way in which massive star formation is different from that of normal stars?
Okay, so massive stars, they're a bit of in a way, they both form through this accretion, this kind of gathering of matter because of gas around this core. The main difference is that a massive star is gonna need a lot more. Well, it's gonna have a lot more mass, and that makes the whole collapse process slightly different. So usually what you have is that your massive star is kind of embedded in this cocoon of of gas and dust, and it's very, very hard for you to see what is happening in this cocoon where the massive star is forming. Massive stars are also different from small stars in terms that massive stars, they actually start burning in their core before they get to their full mass. So in a way, we usually say that the star becomes a star when it starts fusion. And a massive star is going to start fusing, but it's still going to be able to continue accreting mass and getting more and more and more massive. And that's how you form the most massive stars in our galaxy, for example. But if you're a small star, then you're just going to be able to cool very efficiently. You're going to be able to do this very nice, thin, your radiation is just going to blow all material that you have kind of around of your star away. It's going to be very clear for you to see that star formation happening. You can kind of see your little star in the middle and an accretion disk around. Sometimes you can see even little planets starting to form and clear like little orbits around your star. So in what we call protostellar disks. So I think
I have the picture now, yeah.
Yeah. And so in a way, the ways that it changes is, so there you can see that you have like this black kind of orbits, and your star is forming on that kind of brighter central region, and then your planets are kind of forming around it and clearing their orbit as they go along, and that's why it forms kind of these black circles around. So the ways that massive stars and small stars differs, one, it's very easy to see the process of small star formation. It's clear, you can see the disk, you can see everything happen, whereas massive stars are kind of obstructed, our view of them. We have to have things like ALMA to start digging with different frequencies inside that cocoon of dust, where they find themselves forming. And massive stars, they start burning before they actually have their full mass on, whereas small stars, they have, by the time they start fusion, that's their basically the end of their how much mass they are going to get, and they are going to stay with that mass more or less for the entire life of their main sequence, except for the small amount that they lose, for example, by a stellar winds or things like that.
So with massive stars, it's like the beginning, the center of the star is like already thinks it's done and starts fusing, while kind of the remaining part of the star is like, oh yeah, we'll continue accreting, like growing.
Exactly. And that's fine as long as your radiation energy that somebody mentioned, the radiative feedback somebody mentioned before, is not strong enough to kind of push all the material away. Then you can keep on accreting, and that's actually what is going to stop accretion eventually. So as soon as your star is going to start burning more and more material until it burns so much material that the radiation coming out of your star is just going to push everything away, and then it's going to say, okay, no more mass, I'm big enough, let's just stay with this and continue evolving, basically.
Yeah, that's while we're talking about kind of this star radiation pressure things, we got one follow-up question on the neutron star discussion. Will they continue to so inside a neutron star, will they continue to stabilize themselves by continuing nuclear fusion, or will the subatomic particles resist against gravitational forces by just repelling each other at the maximum level? Yeah, so in neutron star, actually, neutron stars are kind of like one big atom core, right? So they are like, so there is nothing to fuse anymore, right? So when you have, let's say you have a proton and a neutron and you will push them together, you can make a, deuterium, and you gain energy, kind of fuse them together. But the neutron star is basically one large kind of object already, like it's already all fused together. And the only thing that's, like, there's no kind of energy generated by fusion inside, because there's nothing fusing, it's just the shear, like the Gammaray pressure, so this quantum mechanics effect that is pulling, like, that stops the neutrons from being in one place and kind of repelling each other. That's actually what's counteracting the gravitational force to some degree. Like, there's a limit to that. I think is it the Chandrasekhar limit at this one, or was the other one?
The Chandrasekhar limit is for white dwarfs.
Okay, I confused them again. Anyway,
Tolman limit is for neutron stars. Okay,
that limit. So as soon as you get over a certain mass, your neutron star will collapse because it can't. This isn't enough anymore. We got one final question here before we are done with the live stream. If the universe is a simulation created by a computer, would studying the universe be computer science, or would it still be with the realms of astronomy cosmology? Well, I suppose in that case, astronomy would be computer science, but it would be quite a different area, right? It would be quite a very different way of studying computers. I think there are some tests you could do for, like, okay, assuming our universe would be simulated by someone, let's see if they did any tricks to, save cost, simulation costs, that you could kind of detect, like, repetitions in the sky, like in the CMB, or like some shapes. But I think we didn't discover any hints for that yet. Unless you know something, Nina.
Yeah, well, I think the simulations, the point of simulations is mostly trying to do what we can't observe, and then from that try to find some hint that we can see if it's actually occurring, in what we can observe. So we can always observe cosmological things in a way, right? Like we can observe the CMB, we can't observe anything before that, but we can also see, like, for example, if you want to study structure formation and galaxy formation, provided that you have good enough telescopes, you can look further to galaxies further and further away, to stars forming further and further away, and eventually that's the same as looking in the past, right? So you can study cosmology in that way. And then if we start being able to measure things like the cosmic web and things like that, then these simulations could give you invaluable information. So for example, there are people that are testing how differently the pattern of star formation would look like, or galaxies would look like in the grand context of the cosmic web. I think Stefan had a really cool image of the cosmic web, or the cosmic web. How would that change if we use different dark matter candidates? And if we can do like multiple simulations in computers, then maybe one day we can go and observe and say, okay, so because of this observation we can rule out all those models, but these models are still good candidates. So I think it's always this kind of hand-in-hand experience. You can't only do in terms of doing it as computer science, but if you're limited only to observations, it's also very hard for you to see what's going on, because it's much beyond what people did like 200 years ago, 300 years ago, where you could actually just take a piece of a few pieces of papers and many hours of your life and just calculate it out. So today we have so much physics all acting together at the same time that we do need to use computers to kind of get a broad idea of what's going on. I think
okay, I realized there were two different interpretations of that questions, and we answered both of them, so that's great. Thank you for being here. Thank you everyone for watching. We are at 1 hour past we started, so we'll stop here. Thank you for all the questions. We'll be back next week, next Monday, same time. So you're welcome to come back and ask more questions. And yeah, thank you, Nina, for being here.
Yeah, thank you for inviting me, Stefan. It was really nice. Thank everybody for the questions as well.
Bye.